Now we are going to talk about conditional convergence. So what is conditional convergence? Convergence. So basically, uh, we know that if we have some series, then if we put an absolute value at every term of our series, then if the new series converges, so which means that the original series converges absolutely, well, it means that, well, the original series also converges, right? So, but what if the new series that we formed by putting the absolute value at every term of the original series, what if it diverges? In that case, the original series may or may not converge, right? So basically we have two different situations. So the original series converges, but the new one does not, or the original series diverges. Well, then the series of absolute values is also going to diverge, right? And we say that our series converges conditionally if it converges itself, but the series of absolute values diverges. So here is an example. So the alternating harmonic series, right? So here an is -1 to the power n minus 1 over n. And we already know that this series converges. We have already shown it by applying the alternating series test, right? So alternating series test. Well, but if we put the absolute value in front of it, so the absolute value of an is 1 over n, and we know that the series, the corresponding series, is the harmonic series, and it diverges, right? So it means that if we put the absolute value at every term, and if this series of absolute values diverges, but the original series converges, then we say that it converges conditionally, right? So more generally, if we have instead of an alternating harmonic series, suppose that I write, I uh, I put p here. So what about the alternating p series? So the alternating p series, so here, if p is positive, then this series converges according to the same alternating series test, right? So then we have convergence. Well, at the same time, um, if p is bigger than 0 but less than or equal to 1, then if we put the absolute value in front of it, then we get just the p series without non-alternating p series. And um, the new series of absolute values is going to diverge, which means that the original series converges conditionally. Right? But if p is bigger than 1, then the series of absolute values is also going to converge because it's just the p series. So then it means that if p is bigger than 1, then um, our alternating p series converges absolutely. Well, and finally, so notice that in this case, if what if p is less than or equal to 0? In this case, our series diverges, but not because of the alternating series test, but because of the limit test for divergence. So we can apply limit test for divergence, and the limit of the underlying sequence is not 0. So our series is going to diverge. Okay, so yeah, so here is the same thing. Um, and basically, we see that given a series, there are three feasible alternatives. So it may be that the series converges absolutely, it may be that the series converges conditionally, or it may be that the series diverges. Okay? So here is an example of a fairly complicated question, something like you will probably see in your exam. Um, so here we're given a series, and we need to figure out whether it converges absolutely, converges conditionally, or diverges, right? So let's figure it out. So the first thing to do is let's try to see whether it converges absolutely, right? So is it true that the series converges absolutely? So if terms of our series are, well, an, then absolute value of an is, well, the same thing without the minus 1 to the power n minus 1, right? So it's going to be just 2n squared over n cubed plus n plus 1. Okay, now the since the terms of our series are just ratios of two polynomials, basically um, the intuition here is to compare it to a p-series, right? So this is something like the numerator is n squared, denominator has the largest power is n cubed, which is 1 over n, right? So this tells us that we need to apply the limit comparison test, and the second series, the one that we will compare it to, is 1 over n, and our series is going to diverge. So here is how it goes, right? So if we introduce a new series, bn is 1 over n, then if we take the limit of an divided by bn as n goes to infinity, well, absolute value of an. So then it is going to be the limit as n goes to infinity of 2n squared divided by n cubed plus n plus 1 divided by 1 over n. So divided by 1 over n means multiplied by n. So times n. And if this times n, I can just replace this n squared with n cubed. Okay, so now I'm ready to compute the limit. So this is the limit of a fraction. So to find the limit of a fraction, I should divide both numerator and denominator by the largest power of n, which is n cubed. And of course, the largest power of n is going to be the same now, because this is how we kind of constructed this, right? So this is how we came up with 1 over n. So precisely so that at this stage, the largest power in the numerator and denominator is going to be the same, right? So this is going to be the limit as n goes to infinity of 2 divided by 1 plus 1 over n squared plus 1 over n cubed, which is just 2 divided by 1 plus 0, which is just 2. So the important thing is that the limit is of the ratio is a positive number. So which means that these two series either both converge or both diverge. And we know that the series 1 over n, when n goes to from 1 to infinity, diverges, which means that the original one also diverges, right? So the series from 1 to infinity of 2n squared divided by n cubed plus n plus 1 also diverges according to the limit comparison test. Okay, so which means that our original series does not converge absolutely, right? So now, is it true that it converges conditionally? We could actually start with the second question, because if we found out, I mean, no, yeah, I mean, if the series of absolute values diverged, I mean, if the series of absolute values converged, then it means that the original series would also be convergent, right? So we wouldn't have to remove the absolute value and test it again. Okay, and on the other hand, if we test the original series and we see that it diverges, then we wouldn't have to repeat for the series of absolute values, right? So anyway, now the question is, does it converge conditionally? And of course, to figure it out, so since we know that without the minus 1 to the n minus 1, the series diverges, um, so the only kind of tool that we have at our disposal is essentially we have two tools. So the limit test and the alternating series test. Right? So let us try the alternating series test. Alternating series test. So there are three conditions in the alternating series test. So the first condition is that um, we should have the multiplier which produces alternating positive and negative signs in front of our series. And we do have it here. So it is -1 to the n minus 1. So check, right? So the first condition is checked. The second condition is that the remaining part of the series should have limit 0, and it should be an eventually decreasing function, right? So let's first check if it has limit 0, because if it does not have limit 0, then it means that our series diverges because of the limit test for divergence. Okay, so let us figure out whether the limit of 2n squared over n cubed plus n plus 1 is 0. Well, and again, basically it is a fraction, so to find its limit, we divide both numerator and denominator. We try to factor out the largest power of n from both numerator and denominator. So the largest power of n in the numerator is n squared, so times 2. In the denominator is n cubed. So here we will have 1 plus 1 over n squared plus 1 over n cubed. All right, so now n squared over n cubed is actually the same thing as just 1 over n. And the limit of 1 over n is 0 times 2 over 1 plus 0 plus 0, which is just 0. So check. So the limit of the our sequence is 0. So which means that the limit test for divergence is not applicable, right? So if the limit were not 0, then our series would be divergent. But since the limit is 0, we kind of need to test it further. And the last step is to figure out whether the sequence is eventually decreasing. Is it true that the 2n squared over n cubed plus n plus 1, is it true that the sequence is decreasing? Well, eventually. It doesn't have to decrease from the start, but it should eventually decrease. Well, how can we do it? So there are basically several ways to do it. And I think the foolproof sort of method is to use a fitting function. Let me show you how to use a fitting function to do it. So f of x, so basically the fitting function is the same thing, only instead of n, we write x. You can write n if you want, and then you will write f prime of n is up to you. So I personally prefer using a new variable, just to remember that now my function is going to be a function of a real argument instead of a whole number. So n, sorry, yeah. So x squared divided by x cubed plus x plus 1. Now what is f prime of x? And basically what we want to find out, is it true that f prime of x is negative for large x? So f prime of x is going to be what? Is going to be, well, 2, I can factor out 2. It's not important. Now I'm going to have a fraction here, right? So I'm going to use the ratio rule. In the numerator, I have 2x times x cubed plus x plus 1 minus x squared times the derivative of the denominator is 3x squared plus 1. And in the denominator, I just have x cubed plus x plus 1 squared. So this is really 2 times x cubed plus x plus 1 squared. Okay, and the numerator is going to be what? Is going to be 2x to the 4 minus 3x to the 4 is minus x to the 4 plus 2x squared minus 3x minus x squared, so plus x squared, and plus 2x plus 2x. Okay, now the question that we really are interested in is whether f prime is negative, right? And notice that 2 is positive, and the denominator here is also positive because it is squared. Well, and again, so x is supposed to be a large positive number. So notice that x is positive here. So which means that the only part that can be negative is this part, right? So the question is it true that minus x to the 4 plus x squared plus 2x is negative if x is large? Is it true? And the answer is yes, it is true. I mean, intuitively, it is very clear, right? So because, minus x to the 4 is that there's a fourth power, and here you have a second power and a linear term, and of course, the fourth power grows faster than the linear term. So x to the 4 grows faster, grows faster than x squared plus 2x as x goes to infinity. So which means that eventually x to the 4 is going to be bigger, right? So hence x to the 4 is going to be bigger than x squared plus 2x if x is sufficiently large, right? So if x is large. So the answer is yes, it is true, and our sequence is indeed eventually decreasing, which means that our series converges by the alternating series test. Now, to make it a little bit more rigorous, so this is probably not very rigorous. So I mean to say that something is grows faster, although it can be made rigorous. But let me explain how you can figure out just how large should x be, so that x to the 4 is bigger than x squared plus 2x. So the idea is that what I'm going to do, I'm going to look to count all the coefficients. So the coefficient in front of x squared is 1, and the coefficient in front of x is 2. So the sum of the coefficients is 3, right? So which means that if x is bigger than 3, well, if x is bigger than 3, then I can multiply this by x cubed to get x to the 4. So then x to the 4 is going to be bigger than 3x cubed. All right. Now, 3x cubed, we do not have a cubic term, so 3x cubed is going to be in turn bigger than 3x squared, right? Since 3x squared is 3x, in order to get 3x cubed from 3x squared, we should multiply by x, and x is bigger than 1, because x is even bigger than 3. Okay, so 3x squared is in fact x squared plus 2x squared plus 2x squared. Well, and x squared is bigger than x, right? So this is bigger than x squared plus 2x. Okay, done. So if x is bigger than 3, then x to the 4 is indeed bigger than x squared plus 2x, right? So here, a large means that x is bigger than 3. So it means that our sequence may or may not decrease until the third term, but starting from the third term and up to infinity, it is going to be decreasing. Well, if you're interested, you can just plot it in Wolfram Alpha and figure it out and see that it is actually correct. Well, by the way, the alternative way, I mean, if you don't want to find a fitting function and differentiate it, the alternative way is to find the ratio of two consecutive terms of the sequence or the difference. Well, what I did here, I actually found this like the nth term of the sequence minus n plus first term of the sequence. And the sequence is decreasing if this expression is positive. Well, and you see it is indeed decreasing. It is actually, this expression is in fact positive, starting up from the second term and on. So the sequence is actually starts to decrease at the second term, not even at the third term. Um, but again, so if you want to make sure that it actually works, you need to simplify this, and here is the expression. And again, so almost everything is positive except for the numerator, and you can see that the numerator is indeed positive because of basically a similar logic, right? Because it has positive n to the fourth term, and negative terms are they have smaller degree. So which means that if n is sufficiently large, then the numerator is going to be positive. So if n is sufficiently large, it means that yes, so the nth term is bigger than the n plus first term, which means that the sequence is decreasing. Again, eventually decreasing, right? So let me just scroll forward because it's just the same thing, only printed. So the sequence is eventually decreasing, and um, the limit is zero, so which means that the series converges by the alternating series test. And since the series of absolute values diverges, it means that the series converges conditionally. Conditionally. Okay, so that was a fairly complicated example. So, but I hope you have learned from it.